So I request the attention of all the respected faculties and delegates. Kindly allow me a few minutes of yours and let me introduce myself and the faculty members of this session. A very good afternoon and warm welcome to one and all. I'm Rituparna from Clarinet, the designated session assistant for a seamless experience, and Clarinet is India's most trusted and widely used digital platform with multiple enriching services exclusively for the doctors. Clarinet is very proud to be a digital partner for this insightful webinar organized by the Department of Community Health and Family Medicine, All India Institute of Medical Sciences, Patna. And the topic for today is multiple linear regression. Now, without wasting any further minute, let's begin today's session, for which I would like to invite Dr. Naveen, sir. Welcome you, sir. So the dice is all yours, sir. Please proceed to coordinate further.
Thank you, Rituparna. Very good afternoon, everyone. It is my pleasure to welcome you all in the 7th webinar on the series Data Analysis Made Easy with JAMOVI software, hosted by Department of Community and Family Medicine, AIIMS Patna, in collaboration with Merit India, Clarinet. Myself, Dr. Naveen Suthar, and I am a postgraduate student from the Department of Community and Family Medicine, AIIMS Patna. I am thrilled to see such a fantastic response to this webinar, with participants registering from the different corners of the country. As we all know, data analytics has become an increasingly important tool in the healthcare industry, allowing doctors to analyze and interpret vast amount of data to make informed decisions and improve patient outcomes. This webinar series aims to provide insight into data analytics and its application to the healthcare. I would like to thank our HOD Professor Dr. C.M. Singh sir and Dr. Shamshad Ahmed sir, Associate Professor of Department of CFM, AIIMS Patna, without whose support this webinar series wouldn't have been possible. Now, I would like to introduce our resource faculty, Dr. Pragya Kumar ma'am, who actually does not require any introduction. However, for those who are new here, Dr. Pragya ma'am is an additional professor from the Department of CFM, AIIMS Patna. And ma'am has over 50 research publications to her credit and has trained over 5,000 researchers across the globe through her knowledge and webinars. With this short introduction, I would like to welcome Dr. Pragya Kumar ma'am.
Thank you, Naveen, and welcome to all the participants in this webinar, which is on linear regression. I think the data file has been shared to you people, and you can download the data file and you can start practicing the commands which we are doing it. So simultaneously, if you do it along with us, then you will find it easy. And those of you who are joining for the first time, for those people, I will demonstrate also how to download JAMOVI, but Dr. Venkatesh has shared the link also in the chat box. So you can click on that link and you can download the JAMOVI software. So before actual hands-on, I would like to demonstrate and convey some of the key points which are important for linear regression. So this linear regression, basically, there are two types of linear regression. There is a simple linear regression and there is a multiple linear regression. So I'll try to cover both these concepts, initially with the simple linear, and then multiple linear is an extension of simple linear with few more concepts. So that I would be telling. So in basic statistics, if you can recall, those of you who have performed the association, basically whenever we try to see the variability of one variable in context of the other, or if there are two variables, how they are related to each other, how they are associated, for that we apply the chi-square tests. And there are various types of chi-square tests. For that, you can again refer to our earlier webinar, which we have conducted on the frequency. And then after that, there's another statistical test, which is known as the correlation. So when the two variables are continuous in nature, so because in chi-square, we need contingency table. What do I mean by contingency table? That there is a categorical variable and you make 2x2 table or 2x3 table, and then you test the association. Whereas if both the variables are continuous variable, or in other words, we call them as a scale variable, then in that case, if you have to see the association, we apply correlation. But correlation, we are not telling you in this session. I assume that you know there are two types of correlation, Pearson's correlation and a Spearman correlation. And if there is a correlation between two variables, and if you want to see the magnitude of that, means unit change of the independent variable, how it is leading to a change in the dependent variable, then we go for a test which is known as the regression. So in advanced statistics, or maybe rather I should not be calling it as advanced, because linear regression now comes as a part of the basic statistics. So how to use these associations or correlation to predict the one variable based on the value of another variable. And also we call it as a modeling, like we make model, and then again we'll see towards the end how we can use that modeling also, and to predict a dependent variable. So the most common statistical technique which we used for prediction in field of medicine is basically, the first one is the linear regression, which is very commonly used. The second one is the logistic regression, which we covered in the last webinar. And third one is the survival analysis, or the one of the method of survival analysis is the Cox proportional hazard model, where we also predict a time to event data. So these are the three methods, and we have covered the logistic regression. We will be telling the linear regression today, and then Cox proportional probably in the next webinar. So again, I started, I think if I recall the last last webinar, there also we have started on the same note, but because the participants, they keep on changing, so we are repeating this example once again. So this is, like you can see here on the screen, there are two columns. So there is, in the one column, it is the distance traveled in kilometer, and there's another column which is the taxi fare in rupees. So if there are 5 data points here, 5 data values, and if I have to make a equation out of these 5 data points, how I can do that? So if I have to do that, what I'll do, that I'll take this taxi fare as a dependent variable, because this taxi fare is dependent on the distance, and the distance you can see here, it's the how much distance traveled. So this formula I have made. So if you replace this distance traveled, like 1 kilometer, it will be 90 plus 10, that is 100. Then for 2 kilometer, it will be like 90 plus 10 into 2, it will be 110, and so on. So this looks pretty simple. Why? Because there is only 5 data point rather, and like we can do it manually also. But if I have to make it in the form of a linear equation, so if you can recall your maths concept in the school time, so there we have studied this linear equation, and the formula of a linear equation is like y is equal to a plus bx. What is this y here? So y here is the taxi fare which we are predicting. So what the variable which we are predicting, that is the y, which is also known as the dependent variable. The second is the a. Now what is this a? A is also known as a constant, and it is also known as the intercept. Then the next is your b multiplied by x. So b is known as the coefficient, which is 10 here in this case, and then x is the explanatory variable. That means the variable based on which you are predicting the taxi fare in this case. So this distance traveled will be the independent variable, which is also known as the explanatory variable. So with the help of this equation, can you predict the taxi fare for a 5 kilometer distance traveled? Yes, all of you please do that. 90 plus 10 into 5. What will be the value? Please write in the chat box if you have to predict a taxi fare for a 5 kilometer. So like Muhsin is writing, Sayan, Navya, and Rohan, Harman, many people there, you are writing all correctly. I think few people are writing in between 450 and 500 also, but that's not true. It will be 140. So if you see the actual value, you can see here that for 5 kilometer, the actual value is also 140 and the predicted value is also 140. So if I ask this question, can you say that the predicted value is equal to the actual fare in this case? What will be your answer? Yes or no? because you have calculated something out of this equation and then you have seen the actual fare. Then can you say that these two are equal? Yes, these two are equal. You are absolutely right. So this is a simple linear regression equation which we have just formulated. But in biological world, like in all our medical science, these A and B, it is not so easily derived from just seeing those columns. So for that, like if you see this table, so you can see there is a distance travel 1, 2, 3, 5, and 2 in one column. And in another column, you can see there's a taxi fare, which is like 96 rupees for 1 kilometer, 112 for 2 kilometer, 123 for 3 kilometer, and so on. So with these 5 data points, can you make a formula for this data? Can you do that? And is it as simple as the previous one, or you are finding it a little complicated as compared to the previous one? So yes, most of the answers are no. Yes, because like I cannot guess. I'll have to enter that in a software and then I'll have to put that equation. Because from like my mental maths, probably people like us, it's not easy for us to make an equation. So how will I do that? I'll put that in software, in even Excel, and then I'll try to figure out what is this A, what is this Y, and what is this. Then you can see here, I have just put these 5 data point in the JAMOVI, and JAMOVI has given this equation. So this is your intercept or the constant, which is 72.56, and this is the distance traveled, which is the 18.7. So here the coefficient has changed. So with this equation, all of you please calculate the taxi fare for a 5 kilometer distance. Yes? Please do it. So you can use your phone calculator. So 162, Manish has written, he's the first one. Then Shubham 163. Yeah, let that maybe it will depend like 18.7. Some of you may take 19. So it will have a range probably. So 160 to 166. There will be a range depending on the value of intercept and distance you have taken. So if you see the actual value, what is the actual value? It is 170. So now can you see that there is a difference between the actual predicted value and between the actual value and the predicted value? And that difference is around 4. If we take 166 highest and if you take like 160, then it is 10. So what is this difference known as? All of you please write in the chat box. This difference between the predicted and the actual. Error, residual, agree. So you have made my task easy. So the difference between the predicted and the actual, it is known as the residual or error. The smaller these errors are, the more accurate our model will be, right? So in the previous example, you have seen that there was no error. Your actual was equal to the predicted one. Like the predicted was equal to the actual one. But here you can see that there is a difference which is known as the residual. So this is the concept of residual in all these linear regression or logistic regression. The analysis is largely dependent on the residual. So now in the previous data set, we have taken only one variable, which was the distance travel. If you take another variable, so now we are moving from, so that was a simple linear regression when there was only one explanatory variable and one dependent variable. But here what I am doing, I am adding few more variables. Like I have taken traffic situation, whether it is slow or smooth. I have taken weekends. Is it a weekend or no weekend? And I have taken weather also, maybe humid, pleasant, or rainy versus non-rainy because it's rainy season here. So with addition of more variables, now I will call, instead of the simple linear regression, I'll call it as a standard multiple regression. Why? Because there are other types of regression also. So this multiple regression is also known as standard, because there are other non-linear regression also, but I am restricting myself to the standard multiple linear regression. So in this case, what will be the equation? The equation will be the dependent variable is the taxi fare, but the other variable would be this A will be there as a constant, then B1 multiplied by distance traveled, B2 will be the coefficient for traffic, and B3 will be the coefficient for weekend, weather, and so on. So there are 4 variables. So this is known as the multiple linear regression, as we have just discussed. Now see this table. So can you find out any relationship in this data set? There are 10 students. This is the attendance of the students. And this is the marks obtained out of 100. So what is the relationship? If you see like attendance and marks, can you find out any? Yes, I'm waiting for answer. So Venu has written attendance increase, marks increase, linear increase. Sayan is writing more attendance, more marks. Yes. So you are right that if one is increasing, that is attendance, then the marks is also increasing. And Santosh is also writing the directly proportional. Apurva is writing, Lalit is writing. So all of you are right. Then Muhammad, Rizwan, Umang, Rahul, Srinath, all of you are correct. And similarly, you again see the next one. In the next table, is it this? What are you seeing in the next table? Table number 2, which is although numbering of table is not there, but can you find out the relationship in this data set? This one, duration of exercise and fasting sugar. Can you see something? So duration increases. Solanki Day is writing proportional, directly proportional, inversely proportional. So you will see that as the duration of exercise increases, your fasting sugar decreases, because you can see here the exercise duration is maximum 55 minutes here. So it is 98, and then again 57, it is 90. But if the exercise duration is 31, the sugar is high. So it is inversely related. So first one was directly related and the second one was inversely related. So both these variables are related. But if you see the sign, if you see the coefficient, you will see that it will be with a negative sign. It will not be without sign. And if there is no sign, that means it is positively related. So that's how we see the association between the two variables. So based on these observations, can we say that we can predict marks obtained by a student if we have their attendance? And can we predict the fasting sugar level of a patient if we have got an exercise duration per day available with us? So can we write that? Yes, all of you are right that we can do that. Now we have added another variable here. So that was if in the previous one it was a simple linear, and then I have again added one more variable, which is the gender. So here the gender and exercise are not related to each other in this case. You will see that because irrespective of gender in this case, if male is there and female is there, so you will see that female is exercising for more hours or more minutes, and male is also exercising for more or less. But here you will see that female are exercising less. So all females are like exercising for less than 40 minutes and all males are exercising for more than 40 minutes. So here the gender and exercise duration is related to each other. So this, we have tried to predict the values of a continuous outcome, and closer this predicted value, better will be the equation, which is also called as a model. So this is just a concept check that we wish to predict a fasting blood sugar level based on gender and duration of exercise. And you have taken 10 individual, you ask their gender, you ask their duration of exercise, and measure the fasting blood sugar level. And then I have used that data to develop a prediction. So which of the following is best suitable model theoretically? So first focus on model 1. What can you see here? Here the actual is 96, predicted is 100. Actual is 1. If I focus here, first focus on these two columns. Then you can see there is a difference between the actual and predicted. Then you focus on model 3. What can you see here? The predicted and actual, they both are equal, like 116 and 116. And then there's a third model where you can see 96 and 130, 132 and 90. So out of this, if I ask, so you are saying model 3, but actually is model 3 really possible practically, is it possible that there is no? Yes, so that is not possible. What is your comment on model 1? 1. Best 3, worst 2. Okay, right. So if you see model 2, model 3, we agreed that since there is no residual, practically this model is not possible. Model 2, you can see that there is a large residual, 132, 90, and then 98, 190, and 105. If you see this, you can see that the residuals are very closely related to very close. That means they're not very wide. So if I see, this is basically the not possible, ideal, but that is not practical. This is a practical possible model. So simple linear regression, till now we have discussed that simple linear regression, which is also known as the ordinary least square regression. This is just another name of this simple linear regression. And it is known as simple because there is only one predictor variable. It is linear because the equation which we are making, that is a linear equation. And then it is a regression because it is predicting a linear relationship, and the value of the outcome variable, it changes linearly with the predictor variable. So now linear regression, if I have to explain what is a linear regression, then basically it is a statistical tool which describes the relationship between a dependent variable and an independent variable. And ultimately, what are we doing here? So we are just seeing, like if you take the example of taxi fare and distance traveled. So distance traveled was a independent variable. So we are trying to see the change in the dependent variable, which was the taxi fare, by seeing the change in the independent variable, which was the distance traveled in kilometer. And the response variable is also known as the dependent variable, and the independent variable is also known as the predictor variable or the explanatory variable, which explains the dependent variable. So these are few terminology in case of a linear regression. Now in this case, you have to tell me. So here there are 4 examples. This is just example of a single continuous outcome variable and single continuous predictor variable. So in this case, if my objective, so let's see the first objective, which is I have to predict a BMI from the observed abdominal circumference. So all of you please write, what is a predictor variable in this case in the first research objective? I have to predict BMI from the abdominal circumference. Yes. So circumference will be your predictor variable. Yes. And what will be the outcome variable? Yes. Mohan, Rahul, Vishnu, Shashank, Sayan, Anis, Rachna, Iftikhar, Kalyani. Okay. Perfect. Now coming to the next objective. Sorry, I have showed you the answer. So you have to predict the heights of sons based on the heights of father. So what is the predictor variable in this case? Father, okay. And the outcome variable is the son. Very nice. Now coming to the third. Dose of medication and hours of relief. So doses of medications are, okay, dose is predictor and the hours of relief is the outcome. Attendance percentage and marks. Okay, attendance percentage and marks. So marks is the outcome, perfect. And then attendance percentage is the predictor variable. So all of you are perfect in all these 4 questions. So now, because you have to identify why these questions were there in your data set, it's you who will identify that what you want to predict and which explanatory variable or predictor variable you want to take. So that the decision making is invested, that process is invested with the researcher. be it a student who is doing a thesis, or a PhD candidate, or probably the guide as well as the candidate can decide together which variable to predict based on the which input or the explanatory variable. So this is a simple equation of a simple linear regression. And you can see here that same equation we are writing in the form of a beta, where y is equal to beta 0, which is the intercept. Beta 1 is the coefficient, and then x is the independent variable and y is the dependent variable. And this is the error. So the lesser this error, the more perfect your model will be. Now we have tried to show you this along with the diagram. So what are these blue points? What are these blue points? Yes, all of you, please write in the chat box. You can see that there is a linear line. This is known as the line of best fit. Yes. So many of you have written this is not the outlier. Rather, this is the fitted line. So fitted line, what is a fitted line? We call it as a fitted line means the line of best fit based on the predicted one. So these values are the predicted. If I have to see this, I will see this 200 and then I'll see the predicted value is the 10. But at the same point, if you see the actual value will be somewhere here. Like you can say 7. So actually these blue dots are the actual values. And this line is for the predicted values. So this distance is basically the residual. So if you have to calculate that, we'll see that. How to calculate the residual. Basically, the statistical software calculates the residual. But you need to understand it, how to interpret residual. So these blue dots are what? These blue dots are the actual value. And this line is what? This line is best fitted line, which is drawn based on the predicted value. So this best fitted line is drawn by the software, taking care that the distance from the actual value should be minimal. And that's why it is called as the line of best fit. So for linear regression, like if you ask from any student, they will come up with this, like you can say this gesture, array, we have to do a lot of assumption testing. Yes, so they are right. If you are doing the linear regression without satisfying the assumptions or without checking the assumptions, then your model is not going to be a valid model and it is not going to be a good model. And even if you submit your manuscript, they will always ask you regarding all the assumptions if you are going for a hierarchical regression or even if you are going for a plain regression. So testing of assumptions are very important. Why? Because you are predicting something. See, whenever you hear this, like from a meteorological department, like they are predicting that rain will happen, they are predicting that there will be earthquake or some other, you must have seen like cyclone and all. The prediction is so good that based on that evacuation plans are made and the people are like, we can prevent a lot of disaster. Why? Because those predictions are very much equal to near. So that's why prediction has got its own value. So similar in medical science also, but that is usually done taking care of all the assumptions. So similarly, if you take care of all the assumptions, it is very likely that your model is going to be successful, or your assumptions, the prediction about a variable is going to be successful. That's why don't feel lazy. I should tell you that in JAMOVI, things are so easy that you only need to put a click to check for the assumptions. But definitely, you should be knowing the output, result, and the interpretation, how to interpret, and what to do if some assumptions are not met. So those decisions are with you people, the researcher, but don't feel lazy not to check for the assumptions, because then ultimately you will have to do that. So now coming to, there are a lot, probably 4 or 5 assumptions, but with practice, you will be able to understand. So these assumptions are like, there is, we know that both the variables are continuous in nature in case of a simple linear. So I'm just telling you simple linear regression first, and then we'll add more variables to make it as a multiple linear. So the one in this case, you know that in case of a simple linear, the dependent variable should be a continuous. And if you can recall the last webinar where we discussed the categorical variable. So in logistic regression, the outcome is a categorical variable, like yes, no, something will happen or will not happen. But here I'm actually predicting a value, which is a continuous variable, and the independent variable should also be a continuous variable. There should be linear relationship between the two variables, and that we will check on the JAMOVI. There should not be a significant outlier. This also we check on the JAMOVI. And there should be independence of observation. So these all, like outlier or linear relationship or independence of observation, all these three we are talking in terms of residual. And whenever I talk about residual, what mental picture you should have? That the difference between the predicted and actual. So difference between the observed. So it is basically observed minus predicted. So observed come first. Why? Because on the basis of that, you will say that it is negative residual or a positive residual. That means the prediction is lesser than the actual or more than the actual. So remember, whenever I say this term residual, the mental image should come to your mind that it is the actual minus predicted. That means observed minus predicted. So all these three, like linear relationship between the two variables, no significant outlier, and independence of observation, all these three we talk in context of residual. And then there's another concept which is known as the homoskedasticity. It is homoskedasticity. Please be patient. We are explaining each and every concept. So don't feel like nagged by these terms, like what is this and how come this heavy term is there. Just be patient and slowly you will understand what are these terms. So now the first assumption, that there should be linear relationship between the two variables. Remember, we in the previous slide, we have seen the relationship between the exercise duration and the blood sugar level, and the relationship between the marks obtained and the attendance. So those were the linear relationship. Because if one variable is increasing, supposed to be, I have not checked that in the, because that should come in the form of a linear regression. So the line will be something like that. So this I have drawn with the taking these data point like gender and duration of exercise and the fasting blood sugar. So here I'm making taking two variable, that is the exercise duration, and based on that I'm predicting the fasting blood sugar level. So if you see this plot will come as a output of JAMOVI. So this is somewhat linear. It will not be a perfect straight line. So, but with experience, you will be able to make out whether it is linear or not linear. So non-linear will be something like that. It is like you can see it is not non-linear, and here it is very much clear that this is non-linear. Linear will be something like this. So this is in graph, you can just see what is a linear and non-linear. So that was first assumption, because it is a linear regression. So that I need to test that whether that linear relationship between the dependent variable and independent variable exist or not exist. Now few more concepts, since now you know what is a residual. So how to calculate residual? So here you can see that there is a best fitted line, and you can see that there are two values here. So there is a value which is 91, and there is a value here which is 2. So now if no, it is not a value, rather it is a serial number. 91 serial number and 2 serial number. So if I have to calculate the residual for these points, how will I calculate? So remember, I asked you that whatever is the actual level, so this fitted value is your predicted one. So I'll see that what is the fitted. So if I draw a straight line from this value, you can see here, this is somewhat a straight line. So this is approximately like you can see here 5.79. And then its actual value, if you see the actual value, what is the actual value? Actual value is this one. somewhere around here, 7.89. So the difference between the observed value and predicted from equation, this difference is 2.18. So remember, we talked that the residual is observed minus predicted. Similarly, here also, if you see this, the actual value is here, somewhere around the 4.8. And the predicted value is 5.35 here, somewhere around this point. So if you take out the difference, then, okay, someone is writing, there is an echo. Okay. Let me check. Is it okay now? Harish? Dr. Harish? Okay, I guess it is okay. Okay, thank you. Thank you so much. So then you can see here, can you appreciate these two differences? Like from the graph, I'm just telling you how to see in the graph. So that is the same which we have shown you earlier also. So this is known as residual and the value is like this. So these two, like 2.18 and 0.557, it is the residual, and this is with negative sign. Why? Because I said that this observed, it should be observed minus predicted. So it is lesser. So it is less. That's why it is in the towards the lower side. So you can see that the difference is the predicted value was less. So this is known as the unstandardized residual. Remember? Now we will introduce few more terms, because in context of residual, you must have seen many times that there is something known as the standardized residual, there is something known as the studentized residual, and then there is an unstandardized residual. So the simple difference between the observed and the predicted is the unstandardized. Now there is something known as the standardized residual. So what is a standardized residual? So basically there are three types of residual. So one is the ordinary residual, which is also known as the unstandardized residual. The second type of residual is known as the standardized residual. So basically, whenever you divide these unstandardized by the estimate of the population standard deviation, that is known as the standardized residual. And in JAMOVI, this function is there. You can standardize your residual, and we'll see this function also. And then there is something known as the studentized residual. When you divide this by the estimate error of residual, so in this case, you take the estimate standard error of residual. So this studentized is supposed to be the best, but this standardized also, many of the equation on many of the analysis is done on the standardized residual. So I hope this concept is clear to you. And this you can see here that the difference between actual and predicted, and this is the residual, which is the actual. And then the next assumption is that residual which you calculate, they should follow a normal distribution. So remember, we talked that here all the assumption testing is done on the residual, because residual are the most important. They are the error. Smaller the error or the residual, perfect, more your model or your prediction will be towards perfection. So you should check again the normality of these residuals. So you can plot a QQ plot here. You can see, and then if they are along this line, then you can say that the residuals are normally distributed. All these functions are there in JAMOVI. I am just explaining you the theoretical background before we actually see the commands. Now there is something known as the variance. So many of you know this, but for those who are like a little confused regarding what is this variance is, I will just try to explain it. So why this variance is important? Because, you know, with mean, variance tells you regarding the dispersion of data. With mean, you cannot say. Mean only tells you the central tendency. Like in this case, you can see these two pictures. If you see the mean value, the mean is same in both these two cases. In scenario 1, it's the 120 plus 140 by 2, so mean is 130. And in the second scenario also, that average is 130. But if I ask the variance, is the variance same in these two scenario 1 and scenario 2? Yes, please write in the chat box. So Dr. Mohan is writing no. Harish is writing no. Ketal, Sayan, Fatima, Dipanjali. Thank you. So they are not the same. Here, I can say that the average height is equal in both the sample, but the variance will not be same in the both the sample. In case of a sample B, the variance is 0. Yes, because there is no variation. Why? Because basically, how do we calculate variance? Here you calculate, you see the distance from the mean. So mean is 140 and the individual value is 130. So it is plus 10, and in the case of this person, it is minus 10. So basically we square it. That's why we call it as a sum of square. We square it and we add it. So the variance in this case will be, and then we divide it by the total sample, like n minus 1. So here it will be, total will be your 100 variance, where in this case the variance will be 0. So for height, we can easily appreciate the variance externally because we are seeing the person and we are making out that, yeah, it's not, there is a variation in the height. Similarly, if you go in the class and if you see the people according to various BMI, you can see that this class has got a very thin individual and very obese people also. So there are some characteristics which you can see and tell. But many times, like biological values, like what we measure, like creatinine and all those biological values, you cannot predict. So for that, you need to do the statistical testing. So now if you see this data set, this is data of 6 individual in data set A and similarly in data set B. Mean is same in both the data set. So what is your comment on the variability, variance? Which data set has got more variance? Yes, please type in the chat box. B. Shubham, Mohan, Anish, Komal, Kalyani, Tandra, Arnab. Yes, all of you are perfectly right that this, although the mean is same, but the data set B has got more variability because you can see here there is a 4 TSH level and there's a 15. Whereas here it is only 9 and 14. So the dispersion is less. So what is a variance? Basically variance, it is a measure in statistics which tells us how the data is dispersed. So this you can see, this is less variance. And if you see the dispersion, this is more variance. So basically there are two types of variance. There is a sample variance and there is a population variance. So population variance is a measure of variability within an entire population, and it calculates how much the individual data point in the population deviate from the population mean. But it is difficult to calculate, so that's why we take the sample variance, and it calculates the population, like you can tell about the population variance taking the sample variance. And then that's why we call it as, if you pick up the sample randomly from the population, then your sample variance is nearly equal to the population variance. So now the next term, you will always say that these many percentage of variance explained, like 10%, 20%. What does it mean? So let's see this example. So if I am investigating the influence of health factors on cholesterol level, and what health factors I have taken? I have taken age, I have taken weight, I have taken exercise hours, blood pressure, how these collectively influence the individual cholesterol level. So suppose a study analyzed these 8 individuals, each having their distinct age, their weight, exercise, and blood pressure profile. And we know the cholesterol level, they are different in the different people, and we want to understand the reason behind this variable. So now the question is, why this variation occurred? Why there is a individual variation from one person to another person? Because the cholesterol level is influenced by a lot of other factors like lifestyle, like behavior, genetics, and each factor contributing to this level of cholesterol. And somehow there is a, together also they are playing some role in determining the cholesterol level of the individual. So if I want to uncover the extent to which these 4 variables, only for me, there are many variables, but I just want to study the 4 variables. that is the age, weight, exercise, and systolic blood pressure, how these are shaping the cholesterol value. So I have calculated, so there is something known as the R. So R, you must have, I think there is some idea to you people that this R is also known as the Pearson correlation. Here, if you make it as a R square, this tells you regarding the proportion of variance explained. So if like R for age and cholesterol is 0.95, so this is basically, it is telling you the individual R between the each independent variable and the dependent variable. And then R square for these are like 0.91, 0.93, 0.35, and 0.84. So can I say that 4 factors together contribute 303% variance of cholesterol? Like I have added all these 4, 91 plus 93 plus 35 and plus 84. Can I add it together? So no, you are right. We cannot add it because although these are acting individually also, but together we have a overlap of factors. So we have got age and then weight and then exercise and then SPP. So all these 4 are acting together, not as individually. And that's why together we take it as a variance. And we want to say that one of the assumption is that this variance should be equal. Now, there is a term known as, you have seen earlier, I uttered a word which was the homoskedasticity. So there are 2 terms, homo and skedasticity. So this is also known as the homogeneity of variance. Homo and skedasticity. This skedasticity is for variance or spread, and homo is equal. So what is homoskedasticity? Basically, it sees that the variances are constant across the line of best fit. That means if you see this, you can see that if this is the line of best fit, the dispersion of these errors should be approximately equally distributed like this. That means they should have a constant dispersion across all levels of independent variable. So in simple term, homoskedasticity, it tells you that the spread of residual or error around the line of best fit is roughly across this, it should be the same across all range of the predictor variable. If you see this here, the distance is less, but as you move ahead, the distance become larger. So that's known as the fanning out. So if your graph is something like this, then your assumption is met. And if your graph is something showing any pattern, then it is not met. So like if you see this, if it's the line of best fit and this is line of best fit, so can we say that the assumption of homoskedasticity is there? So no, because distance is less here and then it has become larger. Again, distance is more here and then becoming smaller. So ultimately, we say that if there is no pattern, then that the assumption of homoskedasticity is met. So how to remember? Basically, you have to recall that homogeneous means uniform. So if it is a homo means uniform pattern and there is no obvious pattern you can identify, then we can say that the data is fulfilling the assumption of homoskedasticity. What is a homoskedasticity? We see the distance, that the distribution of these residuals that should be equal along the line of the best fit. Now, if this assumption is not met, we call it as a heteroskedasticity. So why this heteroskedasticity occur? So basically, when you have got very large range of observed value, like if you are analyzing something as number of patients who are reporting in OPD, that is definitely going to be a very large values and it will have got a large range of values. So then your data will show the heteroskedasticity. So now if your data reports the heteroskedasticity, what to do? So ultimately there are 2 ways. Either you can do another you have to do another way to fix this, that is the weighted least square regression. So I am not covering this weighted ordinary least square regression. But those of you who are interested, we may post some link where you can read it. And then another is the transformation of the dependent variable. So regarding the transformation, there are many ways of transformation, but the most common way to do the transformation is the log 10 transformation. We'll see in JAMOVI how to do that. And most of the time, we transform the dependent variable. So log 10 transformation is the most commonly done transformation in case of the linear regression. These are some of the pictures to show that there is a pattern. This is an increasing funnel. This is a decreasing funnel. And this is a fan shape. So if your plot is showing something like this, that means your assumption of homoscedasticity is not met and your data is heteroscedastic. So till now, what we have done, till now we have checked the assumption regarding the assumption of linear regression. We have linearity, how to test for linearity. And we have seen like we generally do the plotting of residual. We have seen homo versus heteroscedasticity. We have seen how to calculate the value of a residual and what is a standardized residual, what is an unstandardized residual, and what is a studentized residual. So again, how to check for that? So you can do a box plot of residual that will show you, and you have to check for the influential point. And what is this influential point? This is also known as the Cook's distance. So this measure of this influence, it should be less than 1. And I'll explain what is this Cook's distance. So you have to check the distribution of residual, and how we check for the distribution. There is an option in JAMOVI which tells you which is the PP plot or the probability plot, and you can have a QQ plot also of the studentized residual. So that was regarding the residual and regarding the Cook's distance. And there is an option of Cook's distance which tells you like what is the extent of outlier in your data point. Now coming to the, there is another phenomena or the, you can say assumption, which is known as the autocorrelation. What is autocorrelation? So basically, whenever this, first remember that this phenomena is there with the dependent variable. Whenever you try to check a paper, in this example, you start checking a paper. Those of you who assess question like answer sheets, initially you will find for 10-15 answer sheet, you will take more time. And but later when you advance, it will take you less time. Why? Because now you are familiar with the answer pattern, you are with your marking scheme, with your comfort level. So during the later time, there might be a case where the data, it is very much linearly, like you can see that less difference will be there in the marks. So you can see here that there is a, in the previous, you can see there is a 70, 75, 76. And again, the last two, you can see the marks are like only difference of 2 or 1 is there. So autocorrelation is a phenomena basically like with repeated testing or with repeated checking, your later data points are very much correlated with each other. So that should not be there. And to check for that, why it should not be there? Because then it will have a bias in the coefficient estimate and the p-values might be inaccurate, leading to the incorrect conclusion. So what to do, how to check for that? Again, it is not necessary to check for this autocorrelation every time. Why? Because if your dependent variable is something which you are measuring objectively, like in our case, it is the cholesterol level. So cholesterol level is not a subjective measurement. It is something which our instrument or the machine is doing. So in that case, you may skip this autocorrelation testing. This is only done when your dependent variable, like if you are measuring a like something, some domain or some construct using a scale where you are scoring a particular person, like emotional quotient, like empathy, or like maybe quality of life. So in that case, your dependent variable is a variable where it is dependent on the interviewing, because the person is taking the interview. So that case, during the later part, the interviewer becomes very comfortable. But initial 10 to 15 or 20 patients, he will take more time, and there might be some autocorrelation towards the end. So now, once again, coming to those Cook's distance. So here you can see there are basically three types of anomalous data. Anomalous data means I am talking in context of an outlier. So here you can see there is a value which is very away from this line of best fit. So this is an outlier because all the data points are very much near to this line. But if there is an outlier, something like that, then also you will see that the regression line has not shifted much. Can you see there are two regression lines here? One with a bold line and one with the dotted line. What do you mean by these two? Why there are two regression line here? All of you, please type in the chat box. Yes. So there are two regression. Yes. Aditya is right. So that bold one is without the outlier. And if you take this outlier, this has shifted this curve to the dotted one. But you see that there is not much of a difference. The angle is same and there's no much shift to that regression line. Similarly, there is something known as the high leverage point. Now, what is this high leverage point? If you see this picture, here most of the data is concentrated in this value. And there is a one data point which is lying far. So this is known as the high leverage. Here also you will see that the distance is not more from the fitted line. It is very less. But this is away from, if I plot this, so if most of the data point are in this region, this is little away, this one. So this is known as the leverage point. But this again, you can see that this is not shifting the regression line much. So this is known as the leverage point. When these two combine, then this is known as the high influence. No, Robinson. Leverage is not synonym. Like all these three are outlier basically. But we define three types of outlier. One outlier where only the value is very high. The second, this is also, you can say that outlier in terms of, we don't call it outlier, we call it as a leverage. Leverage means it is again shifting because the value is like, it's away from most of the data point. And then like it is much outside, you can say it is much outside the normal range. So the term which we give here is the leverage. And when you combine these two, like away from most of the data point and a large distance from the best fitted, like this. You can see, can you see this? Here it is, if my most of the data point are in this range, then you can see this is away from it and it is having a very large distance, difference between the predicted and actual. So when you combine these two, this is known as the high influence, and that we measure with the Cook's distance. So remember, a high leverage point and a outlier does not affect your regression fitted line much. But your influence, if a data point is having both these two characteristics, then these together, we call it as a Cook's distance, and that will change your fitted line. So you can see here, your fitted line is entirely changed. And this we don't want, because what will happen? Then it will lead to the inaccuracy in the predictions. That's why there is an assumption in JAMOVI where you need to check for the Cook's distance, whether it is significant or not, and it should be less than 1. So, do you agree with this? Are you people with me up till this point regarding assumptions? Okay, so we have seen the autocorrelation, we have seen the homo or heteroscedasticity, we have seen the linear assumptions, we have seen the high influence point, which we measure with the Cook's distance. So Cook's distance is a high influence observation, which is an outlier that has got a high leverage value. Outlier don't move the regression line much, neither do the high leverage point, but something that is both an outlier and a high leverage has a big effect on regression, and this is known as the influence, high influence, and we operationalize this in terms of a Cook's distance. This is just the summary what we have discussed up till now. Now coming to the interpretation of beta coefficient. So the value of beta 0 here, or the value of y, it is the value of y-intercept when your x is 0. Similarly, the value of slope is the increase in the mean of y for a unit increase in the x, controlling for other predictors. We'll see that in the actual data set. And because we are interested to compare predictors in terms of the magnitude or of their effects on response variable, so we have an individual beta coefficient for each of the independent variable. So now if we come to the hypothesis testing, what is the null hypothesis in case of a regression? So here null hypothesis is in the form of a beta, that is the regression coefficient. So we say that the beta 1, because if it is a simple linear, there's only one coefficient, that will be the 0, and the alternate hypothesis states that the slope will not be equal to 0. So we'll be seeing the statistical how to check in the JAMOVI. So we'll see have to predict the cholesterol level based on the body mass index. So I'm first going with the simple linear regression, and then we'll see the multiple linear regression. Before I actually go into the demonstration, there is another concept which is not applicable for simple linear, but if you have got more predictor variable, then you have got something known as the multi-collinearity, and I'll discuss that. So before that, the next webinar is on 14th November on survival analysis, the same time, Tuesday 2 to 3:30 p.m. Before I show it in JAMOVI, let me tell you few more words of this multiple, or should I tell them first the demo of... So I'll demo first the linear, simple linear, then I'll come to that. Otherwise, it will be very heavy for you people listening continuously for 1 hour. So those of you who have not downloaded JAMOVI, how to do that? Go to Google. This is just my Google, this thing. And then you can click. Dr. Venkatesh has already pasted the link. You can write download JAMOVI. And then if you click, it will lead to a site which is the JAMOVI desktop. You can click that, and then you can see that there are two versions. There is a solid version, and then there is a current version. Yes, Surbhi, you will get all the PPT, all the like recordings also. The data set is there with you. And there's a request from Clarnet team, because generally it, I don't know, because of the various administrative reasons, there's a delay in providing the videos. So if you could do it like relatively in lesser time, it will be useful for the participants. Because we receive many mails. Yeah, Rituparna, are you saying something?
Yes, ma'am. I said that I will be definitely looking into this with my concern.
Okay, yeah, thank you. Because generally, it's the curiosity of a student. Like if I have attended something today, I want it to revise maybe within 2 to 3 days. so that the concepts are like I can do that. So just a request from you people. And thank you so much. So PPT, yes, we will share the PPT also. So you can see here that there are two versions. There is a solid version and there is a current version. So we generally recommend all of you to install this solid version. But I'm not installing it. If you click this, and again, there are two types. You can see there is a window version and there is a, for those who use this Mac, there's a Mac version also. So you can download that depending on your like specification of your laptop. Then I am opening again in the previous workshop also there was an issue with the opening of the data. So how to open once you have downloaded that, it's very simple, like you have to click next and it will be finished, and then that is there on in your drive. Then again you have to type JAMOVI here. If you type JAMOVI on window icon, you can see here it will show you, and then you click, if you click this, it will be open. So I am just showing you how to import the data. Have you provided them the JAMOVI data or the Excel?
Excel JAMOVI.
Okay, so we have provided them the both the version, the Excel version also, or the JAMOVI version also. So if you click this, a blank data set, this thing, a blank template will be opened, and then you can see that you can import the data. So how you can import the data from Excel? You can go to this tab here, click. We have shared the data. Dr. Surya is asking. Okay, Dr. Venkatesh, can you please send the link, or Naveen, Dr. Naveen, if you can hear me, can you please share the data again here? So then again, you can see here, I have to open the data set. So I'll click this open. So if you click this open, again, please be very cautious here, because last time there was a participant who had a hard time in importing that. And what she was doing, here you can see, there are two icons, this PC and library. So you see this is blue. So if blue, that means you are giving the path to this PC. So she was there in the data library, and then she was trying to import, but that was not, that could not be there because of the problem. So that's why you click this PC. Data library means that if you click this, JAMOVI has got these data set where you can like open these data set and practice. But you don't want to open the data set of JAMOVI. So go to this PC and then show it a path and go to browse, and like then you can go to any of the, let me go to any files probably. I'll go to this my drive. I'm just showing a path where to download the data set. So let's see, this is for JAMOVI. So I'll go to this JAMOVI, this webinar, and then today's linear regression. So like shared with participant, this is the folder. You can see these are the two data files, and it can, if you see this, it imports all data file. Even the SPSS data file, you can see SPSS, R, Stata, and Excel and all it does. So if you click that, it will be imported. So this is regarding, so be careful to click this PC. You don't have to import from the JAMOVI library. So are you people clear on that? Then I'm closing this because there is already, and then this data. So this is the data set which we have to demonstrate. So now if you see the JAMOVI interface, in the same interface, you will have the data set as well as the output. So now you can see here, it is a list of variable. So all these variables are there. And if you keep on clicking this is the description of variables. So if you import the data, many times you need to change these measure type. Like age is continuous, it is in the decimal. So maybe I want it is in integer. So I'll change it to that. These two clicks are like forward and backward. If you keep on moving this is again gender nominal. Again, I'll go on to this race. Then next is the BMI. Similarly, I can go like that. And then you can see here, if you close this window will be closed. So like this is the variable. And then coming to the data, this is again, these are the data. And this is in the variable section, you will see, and in the data that there are options like compute, transform, there's an option of filter. So you can go to our earlier webinar where you can see these because we have carried out all the webinar on all these tests. So you can refer to those webinars and you can learn, those of you who have not learned. And then come the today's session that is on the linear regression. So I think one participant is writing that they are not able to import data. Okay, so it is data set we are sharing. So Sanskriti, you can like we have shared it again. And then you can see here that I have to perform regression. So there are two variables here, simple linear, cholesterol based on BMI. So I'll go on regression. You can see there are many options. So I have to click the linear regression. So if I click the linear regression, then this window will open. You can see here there is a dependent variable and there are two boxes. So this covariate is all for continuous variable and this factor is all for the nominal variable. So I will move this cholesterol to the dependent variable and this BMI in the covariate because this is a simple linear. Then you will see that this table is getting populated. Now, before I go, what we did that we have to check for the assumptions. So assumptions, if you can recall, there are these many assumptions. So what is the autocorrelation? Yes, please type in the chat box what we did in the autocorrelation. How do we check for autocorrelation? So autocorrelation is basically, it is the property of a dependent variable when the measurement, like near measurements are very much correlated with each other. Examples are like marks, which we check the papers, or any variable where there is some subjectivity. But here, in this case, we are measuring cholesterol. So you may not click this. But again, just for interpretation, I have clicked this. So if you click this autocorrelation, it will lead to a table which is known as the Durbin-Watson statistics. If you focus yourself here, you can see the Durbin-Watson statistics. And what we did that this test statistic should be less than 2. That means this p-value should not be significant. So that's why there is no autocorrelation in this case. So this assumption is met. Now coming to collinearly statistics, since there is only one independent variable, so I'm not clicking this. Now coming to these three. So there is a normality test, there is a QQ plot, and there is a residual plot. So I'll check this normality test. Normality test is generally, it is the Shapiro-Wilk test, which this JAMOVI gives. So this is significant, but normally we always say that Shapiro-Wilk is used when the sample size is less than 50. Since it is more than 50, so I'll go for the QQ plot of the residual. So if you see the QQ plot of residual, and then there is a residual plot. So this, by clicking this residual QQ plot, you are checking for the normality of the residual. So that was one of the assumption that the residual should be normally distributed. So if you see this, how will you see that the data, most of the data points are along this diagonal. That means it is approximately normally distributed. Now clicking the residual plot, this residual plot we click to check for the assumption of homo and heteroskedasticity. So this is the residual plot. If you see this is the overall, like this is the fitted value. Remember, on the x-axis, it is the fitted value, which is the predicted value. And this is on the y-axis, it is the residual. So you have to check like this is the 0 point. So above and below, it should be, there is no pattern. So you can say that there is no pattern. Here also, if you check the residual, you can say that there is no specifically, like remember we discussed like fanning out and all. that pattern is not there. So I can say that the assumption of homoscedasticity is met. Now coming to the Cook's distance, if you check with the Cook's distance is the value. So the value of Cook's distance is 0.01. So it should be less than 1. So that assumption is also met. So because all my assumptions are met, I can go for that model fit statistics. This is reference level. This is used when one of the variable is categorical in nature. But here, there's both are continuous, like this BMI is continuous. So that's why I'm not clicking this reference level. Coming to the model fit, you can check with the overall model fit with the F statistics. You can click on this adjusted R square. That will tell you regarding your model. So if you see this is R square. R square is 0.17. What does it say? Or adjusted R square? That means it says that 17% of the variance in the cholesterol level can be explained by the changes in the BMI. And this you can see that overall it is a fit model. And this, it tells you the estimate. This estimate is the intercept. And this is the coefficient, 4.28. So you can say that if you increase 1 unit of BMI, your cholesterol changes with 4.28. Now coming to the model coefficient, here also you have to, this is the beta. But if you want a standardized beta with 95% confidence interval, you can click that. And then this is a ANOVA test, which will again give you the value of your model fit. So this is the overall ANOVA. It is again telling you that this is your model is fit because the p-value is less than 0.001. And here you can see the same intercept, and this is the standardized estimate. So there are two things, estimate and standardized estimate. This standardized estimate is basically when you standardize your residue, this beta coefficient, this is known as standardized estimate. And then you can again click this, come to this save. So if you click this save, you can see here there is a predicted value. So just if you want to check, you can check the predicted value and residual. If you click these two, there will be appearance of the two variables in the data set. So you can see this is the predicted value and this is the residual. So if cholesterol, you can see the difference. If I'm focusing on this person, probably. So the actual value of cholesterol is 261. The predicted value is 241. So remember, we discussed that observed minus predicted. So the residual is 19.922. So this is how you can check there is a residual for each of these cases. And this is just to show, and this is the predicted and residual. So then how to interpret? So we have learned the interpretation, the assumptions we have seen, the overall model we have seen, the Cook's distance, the autocorrelation, the QQ plot, and the residual plot. So any questions up till this point? Then I'll go to the multiple linear regression. Okay. So if not, then we'll again go to the interpretation. You know now how to interpret. So now going to the multiple linear regression. So multiple linear regression is an extension of the simple linear regression, where you have got more than one variable. So like you can see here, there's a x1, x2, and xk, and this y is the dependent variable. So moving ahead for predictions, if we want to know whether it is possible to predict the SpO2 level, like if I want to predict SpO2 level, and I have taken like 6 variables: age, gender, smoking status, fever, respiratory rate, and duration of breath hold. So then what will I do? So because there are many predictors variable, and I have to predict the SpO2 level, and that prediction is again a continuous output. So this is known as the multiple linear regression. Why multiple? Because there are more than one predictor variable. Why linear? Because the value of outcome variable, it is changing linearly with the predicted variable collectively. And regression, because the equation is in the form of a linear regression. So the underlying assumptions are same as we have seen. Like the dependent variable should be continuous. There should be one independent variable which can be continuous or nominal. There should be independence of observation, means there should not be autocorrelation, which we check by the Durbin-Watson statistics. There should be linear relationship. There should be homoscedasticity. And then like outlier and leverage point and normality. The only thing which we have not discussed up till now is the multicollinearity. And multicollinearity happens when there are more than one independent variable. That too, mostly it is with the two continuous independent variable. And we'll see what is this multicollinearity. So in this case, there is an important point to remember that if you have an ordinal variable as one of your independent variable, then this linear regression does not treat that ordinal variable as ordinal. So either you will have to take it as a continuous or you have to take it as a nominal variable. So ordinal nature of a variable or that interpretation is not maintained in case your independent variable is a ordinal variable. So for multiple linear regression, like I'll be showing you the cholesterol level based on the age, gender, BMI, and SBP. So again, these are the same linear relationship which we have discussed. Now, only one concept which I wanted to tell, that was regarding the multicollinearity. So what is the multicollinearity? I said that the two independent variables should not be highly correlated with each other. Because what will happen? If they are highly correlated, then that means the one change in one, it is getting influenced by the other. And then there will be a problem in understanding which independent variable contributes to the variance explained in the dependent variable. And it will also have issues in the model, because we always want to have a less number of predictor variable. If you have got many variable, then the model is going to be a difficult one. So there is always issue between the balancing the accuracy of model and taking the number of predictor variable. And then there's the issue of sample size also, because for linear regression we always say that at least there should be minimum of 20 outcome, 20 sample should be there per independent variable. So that's why we don't want this problem of multicollinearity in our model. So it is a situation when there are two or more independent variable in a regression model which are highly correlated with each other, then we say that it is redundant. That means we are not giving any extra information by taking two variables. So let's understand this multicollinearity with few more examples. Suppose I am predicting cholesterol level. So let's consider a scenario where I want to predict a person's cholesterol based on the various health related feature and how I can introduce multicollinearity. So if I am taking weight also, and if I am taking the BMI also, then definitely this weight and BMI, they are going to be very much correlated, because this BMI has got this weight also inside it. So they will be okay. Yes, we are. I think there is some issue with the video. Okay, we are checking on that. Please bear with us. And then, but I'm audible, so you can focus on my voice till the time it gets corrected. And then you can see this weight and BMI. Yes, Dipanjali, confounder, we define confounder in a different manner actually. Because we don't say that it will be a confounder, because those of you who know the confounder, you know that it will not be a confounder per se. Rather, we say that it is correlated rather. and it will give you a redundancy by taking that. So this we mean by the highly correlated. Now again, if I want to predict a person's heart rate using the exercise based on different attributes, then there might be a scenario when age and resting heart rate, they will be very much correlated with each other. So that's the problem of multicollinearity. In that case, you can replace, like you can remove one variable and you can keep the other variable. So that's why you can say that this is like a multicollinearity, age and the resting heart rate. Whereas in the previous one also, you can say that the BMI and weight will be your multicollinearity. So they are very much correlated with each other. So how to check for those multicollinearity in case of a JAMOVI or for that matter, any software? So basically there are two values. So we see either you can see the correlation coefficient. So that should be less than 0.8, or here as a part of this JAMOVI output, it gives you the tolerance and VIF value. So VIF is the variation inflation factor, and the VIF value should be less than 10 for each of these variable. Now, before we go into the multiple regression, let's see how the various articles they have reported the multi-regression table. So this is one of the article which is the determinants of quality of life during induction therapy. So what is the predictor? In this case, what is the dependent variable? So dependent variable is the quality of life, and then there are other predictor variable. So you can see here the purpose that just see the pink highlighted one, that the quality of life is impaired during maintenance treatment. So they have taken the proxy reports of child health questionnaire and the PET-SQL cancer version, and then they have calculated, they have taken the various variables like child functioning, role limitation, mental health, behavior, etc. And there you can see that they have taken, so can you see there are a scale like role limitation, bodily pain, parental impact, and they are the other variables like determinants. So how many multiple regression analysis must have run to provide this table? Yes. All of you, please see that. How many multiple regression? So you can see there's a role limitation. There's a bodily. So these are what? If you focus on this, these are what? So these are the dependent variables. So there are 4 dependent variables: role limitation, body pain, and they are the predictor variable for each. So there are 4 regression here. So for bodily pain, these are the variables. For time, these are the 3. So now can you identify how they have given? So there are 4, yes. Sayan, Rizwan, you are right. And then can we make a model equation from this table? Can we make a model equation? What is your idea? So for model equation, what do we need? We need an intercept, and we need basically the coefficient. But can we make it? So here, if you see, we don't have an intercept, so we cannot make a model equation from this table. So now this is another multiple linear regression. You can see to evaluate the relationship between the health literacy and state other study variable. So here they have taken the other variable like the gender, smoking and all. And this is the regression coefficient, standard error and the significance level. Again, there was one regression analysis where they have studied the factors associated with the delayed diagnosis. So the dependent variable is the delayed diagnosis, patient delay, which they have measured maybe in some days. And then you can see like family income, previous breast symptom and smoking. And they have given you the univariate and multivariate. So basically it is univariable and multivariable. Univariable is the simple linear regression, and multivariable when you have got multiple linear regression. So this was another. So this is how the various this thing they have like reported. So I can see few hands raised. So when should we take questions after demonstrating? the linear? Okay, so please wait, Maheshwari and few more people. 5 more minutes and then we'll take questions. So this was the JAMOVI, and here if in the same simple linear regression, if I take more variables, so apart from BMI, I'll take gender also, and maybe you can take systolic blood pressure also here, or age. Yeah, better to take age. So I'll take age here, and then I need to check one more assumption, which is the collinearity statistics here, because there are more than one variable as an independent variable. And if you see here, the collinearity statistics appears in the form of the VIF and tolerance. And all the VIF, actually tolerance is the opposite of VIF, means 1 by VIF is the tolerance. So VIF should be less than 10 and all the values are less than 10. And then you can check the other, this thing. So here the model is again significant. R square is now 18%. So initially with one variable, it was 16%. With addition of two variable, your model has improved marginally, only 0.02%. And then you can see the various p-value. So BMI is significant, but if you see the gender and age, the p-value, so they are not significant because p-value is, that's why you will see that there is a marginal improvement in the model. And if you want to see the this one, then you can see this BMI, again, this is the same p-value and standardized estimate. This is gender. Here you have to do the interpretation. So how you will interpret it, although it is not significant, then you can say like -12. -12 means it gives you the value of cholesterol in male, taking the reference as female. If you want to change the reference, then you can go like this. You can change the reference level from here. But I am not changing it as such. So it is telling you the value of reference or value of cholesterol in male. So -12 means the value of cholesterol will be 12 less in male as compared to female. And this is these are the other, we have discussed the interpretation, and the Cook's distance also you will see that it is less than 1. Assumptions check, we have Durbin-Watson statistics you can see here, but it is not needed in this case. And these are all like QQ plot for normality of the outlier. And these are the residual plot for the homoscedasticity. So yes, I think we have covered all these assumption checks and everything. And now we may take questions. Oh, weights. Yes, Jyotsna is asking weights. I will tell you before, optional when to use. Yes. So I'll take your question first. So weights here is basically, remember we discussed that if you don't satisfy the assumption of homoscedasticity, then one way to fix is the weighted least square regression. In that case, we put weight here. Now the next question is how to decide for the weights. So do you want me to tell that, the weights? So there is another command. Based on that, you decide the weighted this thing for all the residuals, and then you put that variable here in the weights. That is another regression which is known as the weighted least square regression. Jyotsna, is it clear to you when to use that? So it is used when the assumption of homoscedasticity is not met. So yes, any other? I think there are many hands raised, Rupam and Maheshwari. Which one? This one?
Model.
So Cook's distance. Somebody asked Cook's distance? Yes. So can you, like, how will you ask the question? Do you want to unmute and say, or what is the option? Or you can paste in the chat box. Rupam, yes, what is your question? Can you see the chat box? So we are seeing, but I think. Yes, Like learned team, can you guide me how to ask, how they will ask? So there's a separate option in D chat box. Okay, D
Yes,
chat
ma'am.
box. Okay, can you show me that?
Okay, all right, ma'am. There's a
Okay,
box, ma'am.
okay, Q&A, there is a, okay, okay.
I'm posting it on the chat box, ma'am, so that you can see it. Okay.
Okay, okay, yes, because I have just opened the normal chat box. But in question and answer, I cannot see that is refer relief time. They are just responding to the questions which I asked. Can it be offline available later? So which one? Offline means like data set?
This question
Okay.
was posted by Dr. Navneet Kapadia.
So Dr. Navneet, offline means like are you talking of the workshop or are you talking about the data set? So I'm not, can it be? What is it in this case? Can you define this it? Offline available means I'm not able to understand. Probably you can refine your question. Then Saurabh is asking, okay, write up. Anju's write up. Okay, I'll show that. And Saurabh is asking explain residual. So residual you want to, okay. So I'll explain here. So residual, like in this case, let's see this example. I have clicked the residual and predicted value. So if I go to the data set, can you see here this column? So what is this column? This column is the actual value of cholesterol. And this is the predicted cholesterol. So the residual is actual minus predicted. So I'll give you this question. You calculate the residual for case number 2. So the actual is 0.79, sorry, 279. And this is 240. If you take like whole number, 240. So what is the difference? It is 38.03. So this difference which you can see here, this is basically the difference between the actual and predicted. That is known as the
connection.
Let me check. Okay, am I audible now?
Yes, ma'am, you're audible, but sometimes your voice is
Still?
breaking, ma'am.
This is right.
Ma'am, you're audible, but your video is and voice is getting stuck, ma'am, in between.
Let me check the, let me go to another. No, again it is. Yes, so am I audible now?
Yes, ma'am, you're audible now.
Okay, sorry for the inconvenience. And now I was explaining you the residual. So this, can you see there are two columns here? The actual value of cholesterol. So this is the actual value of cholesterol. This one. And this is the predicted value. So let's say you take this case. Case number 9. So what is the actual value of cholesterol? It is 177. And what is the predicted value? It is 207. So what is the residual? So actual means 177 minus predicted, which is 207. That is minus 30. That is the residual. That means the difference between the actual and predicted is the residual. And if it is less than that, it will be a positive residual. If it is more than that, it will be a negative residual. That's the concept of residual. The difference between actual and predicted. Is it okay now? Have you understood? Yes, Sayan, I'm telling you the normality. Before that, Saurabh, okay, Saurabh has understood this. So now the next question. Our next question is normality. Okay, so normality testing is basically done using a PP plot or a QQ plot. Here, there are two types of normality testing. Okay, Anju, I'm coming to all those two questions. You have asked me to write the interpretation and log 10 transformation. Both I'll show. So this normality testing is basically, there is an option here, which is the normality test. So normality test is done. If you click this, it will give you the value of a Shapiro-Wilk statistics. So you can refer to our earlier webinar. You can, but if you don't want to, then I'll explain here. Here you can see there is a statistics and there is a p-value. So Shapiro-Wilk statistics is an objective way, and if its p-value is less than 0.01, we say that the normality assumption is not met. So basically here we don't want our p-value to be significant. But this is applicable if your data is less than 50. That means if you have got a small data set. If you have got a large data set, then it will always be significant. That means it will always show that there is no normality assumption is not met, but actually the normality assumption is there. That's why I later said that you don't need to click this if your sample size is more than 50, because then it will be not a true depiction of the normality. So that's why I have unchecked this, because this there, if you see the QQ plot, my data is normally distributed. But this Shapiro-Wilk statistics is showing that my data is not normally distributed. So you click only that normality, this thing, if your data is number of sample is more than 50, then you go for the QQ plot, not for the normality testing. That is the Shapiro-Wilk. So is that okay, Sayan? Then I'll go to another question, Anju. So Anju, yes, let me show you the interpretation, how to write that. So like this was the interpretation which we have written for the simple linear. You have to make table like this, where you are writing the constant BMI, 95% CI of that beta, T value and P value, the R square, and the Durbin-Watson. And then you can write the interpretation that the linear regression was run to predict the effect of BMI on cholesterol. A scatter plot, it was showing that it was linearly associated, and then visual inspection is also showing, and then homoscedasticity and normality assumption was met. So in the result, you need to write regarding the homoscedasticity and normality. And then I have form this equation, and then I have written that BMI was statistically significant predictor for accounting for 16.6% variation in the cholesterol concentration, and one increase of BMI leads to 4.3 millimole increase in the cholesterol concentration. So this was regarding the interpretation. Now coming to the log trend transformation. So if you have got concept of this homoscedasticity is not met, then there are two options. Either you can transform the dependent variable, or you can use this weighted least squares regression. So if you want to transform this, there's an option, you go to the data, and here there is an option of compute. So click this compute, and then you can see there is a function here which is fx. So in fx, there are many options. This is absolute, exponent, log, log 10. Click on this log 10 and then select variable from this box. So this box, like my dependent variable in this case is the cholesterol. So I'll click this cholesterol and then I'll close this. So you can see this K column, it is showing the log 10 transformation of my dependent variable. Okay. So Muhammad Hussain is asking me to repeat the residual once again. So residual, yes, okay, I'll do that. So residual is again the difference between the predicted and observed. So if you like go see these values, this is the actual value of cholesterol. So this you can see, this is the actual value. You can take any individual, and it is better that if you do it. If you do it on your own, then it will become very clear to you. And these two sections are for the residual. So basically the difference between the residual and the predicted difference between the residual and the actual value is known as the residual. So Rahul is asking how to use a non-continuous nominal data type in a regression to predict outcome. So it is like, then you'll have to go with the binomial regression. You are asking about the, okay, as an independent variable. So yes, it will be like I said, na, either it will be like 12. If you take the gender here, I have told this, but maybe you have missed. You take this gender. It is writing like minus 12. So you can say that the value of cholesterol is 12 lesser than female in male. So reference is female. So if I am telling in male, I'll say that all men will have a 12 millimole cholesterol lesser than the female, or other way around. All female will have a 12 millimole cholesterol more than the male. Okay. Okay. Keta is writing collinearity versus autocorrelation. Autocorrelation is in context of a dependent variable. In this case, cholesterol. If you are measuring that, so with repeated measurement, your variable might, like your measurement will be very much similar. So that is autocorrelation. That's why it is called auto. Means one variable inside that there will be correlation between the residuals. Whereas multicollinearity is between the two different independent variable. Like in this case, if I have to explain, the autocorrelation will be in the cholesterol. Like if it is some subjective measurement, like if I am measuring skin fold thickness here, then it will be autocorrelation. But the collinearity, multiple collinearity will be between the BMI and age. So Keta, are you clear between the multicollinearity versus autocorrelation? Okay. Thank you. Any other question? Any more questions? Okay. So you can write to us at the support meritindia.org at gmail.com, and we will answer that. You can post your questions in the group also. And I hope this session is clear to you. The recording will be available to you people for future reference as well as the PowerPoint. And then see you in the next webinar, which is on the survival analysis. Okay. So thank you. And I think over to Naveen.
Thanks a lot, ma'am, for this wonderful session. I hope all our participants had benefited out of today's webinar. It was a very interactive session, ma'am, and we will be sharing the e-certificates and resource material to your registered email ID in a week's time. And we would like to share that you should visit our website, meritindia.org. Follow us on the YouTube. Our channel name is the Merit India, and kindly install the app Merit India to your phone. And our next webinar on this series will be notified on your email and we will be sharing the links with you shortly. As the last part of the today's webinar, I would like to invite Dr. Shamsad Ahmed sir, Associate Professor of CFM Department, to deliver the vote of thanks. Over to
Yeah.
Dr. Shamsad sir.
Thank you, Naveen. And it was a wonderful participation from all. And actually, there are lots of questions, and I think first time, it's second time we have extended 15 minutes because of so much questions are available there. And actually, we want to answer all these questions, but due to time limitation, we have to end this webinar right now. But in any case, if you have any query, you can reach us directly, or you can mail us at support@meritinia.org. We will definitely answer all use query. And do join us our next webinar on survival analysis. And okay, thanks a lot to all participants. Thank you.
Thank you so much. And thank you to the Clarinet team.
Thank you, sir.
Dear
Team
doctors,
Planet,
for
we can close now.
yes, sir. Very wholehearted thanks to all of you for extending us the opportunity to host the session, and it was really great. So, with all your permission, now I am closing the session for today and looking forward to host you again very soon. Till then, stay safe and healthy. Thank you, everyone.